All right, what's up, guys? So, continue on with chapter 3. This is chapter 3, section 2. We're going to talk about combining matter. So, this is staying in the idea of chemistry, and we're going to keep talking and discussing about it. So, let's talk about combining matter. This one's a little long. Apologize for that, but it's got to be covered. So, here we go. So, compounds, okay? So, compounds is just, it's composed of atoms of two or more different elements. So it's pretty much you take two different things and you combine them together to make a compound. And all compounds, compounds have different properties from the elements of which they are composed. And we're going to spend some time talking about those today. So within this, first important part to know is what a chemical formula is. And that's a way for us to represent compounds that will use symbols and will also use subscripts of numbers to let us know how many of those atoms of a certain element are in that compound. And it's kind of like in math class that if there's not a number next to it, just like if you have X, it's understood to be a 1 in there. So that's what you'll look like with those. So within combining of these things, you're going to combine these things in different ways. There's different types of bonds that'll form whenever you're combining atoms together. So one big one is a covalent bond, and a state of stability can be achieved from elements forming chemical bonds. And that's the reason to do this is that what it'll do is it'll lower its potential energy and make it more stable. And that's what these things are looking to do. These elements are looking to do. And that's what they'll do. And that's what builds literally everything that you have around us, even us including. We're made of atoms and how those atoms interact. And it builds into um, atoms to compounds to molecules, and it keeps just expanding and building. So what you'll see in this is that chemical bond is the force holding together elements in a compound. So the attraction of two atoms for a shared pair of electrons that holds the atom together is a covalent bond. I really don't like the definition that they give here. What I would rather really push is that covalent bonds are elements. Covalent bonds are bonds between elements that share electrons. That's taking it to where you'll understand it. That's what I think it's good for. In this example here, that you'll see is the nucleus of each atom has one proton. So there's one. And the two positively charged protons attract two negatively charged electrons. But here's the thing is you see that these guys are being shared. Okay, those electrons are being shared between the two. So they can get that thing, we call it a full outer shell, and have full valence. That's what they're looking for, and that's what takes place within there. That's what a covalent bond really is. So I'm sharing those electrons to get a full outer shell. Within this, covalent bonds build what we call molecules, and all that is composed of two or more atoms held together by covalent bonds. All molecule is. And a compound comprised of molecules is called a molecular compound. Learning some terminology here. This will help you your 11th grade year if you decide to take my chemistry class. Then within this, we have polar molecules, and when this happens, when there's not an equal share. So sorry about that. There's not an equal share of electrons equally, resulting in the electron spending more time near one atom than another. This unequal sharing results in these polar molecules, and it gives it special properties for those molecules. So within these, it's just a good example of one. Like here is a water molecule is a really good example of a polar molecule, because what happens is it builds these hydrogens don't have as strong as a pull on that electrons that's been shared. So what happens is those electrons, which are negatively charged, spend more time with the oxygen. So what it'll build is a what we call a partial negative charge, which you can see here. And since there's less electrons there for the hydrogen, it builds a partially positive charge, which you see there, and it gives water all of its special properties of it. An ionic bond is the attractive force between two ions of opposite charge. Compounds formed from ionic bonds are called ionic compounds, and they are formed from two separate types of ions, cations and anions. So a sodium atom, it tends to lose a single valence electron, and a chlorine atom tends to gain a single valence electron. So what happens is sodium loses that electron. And when it does that, it loses a negative charge, which means it has more positive charges, which forms a cation. The chlorine gains an electron, which means it now has more electrons than protons, and it forms a negative ion called an anion. So in this attraction is between opposite charges. That's what builds this ionic bond, and it is very, very strong. It is very, very strong. It's the strongest of the type of bonds we're going to discuss. So then we have metallic bonding, and metallic bonds, those are really cool because it gives metals all of its properties that you see we use metal for around us in our lives. Even as simple as you to charge your phone is metal bonds. That's exactly what it is. So in metallic bonds, the positive ions of the metal are held together by the attraction to the negative electrons moving among them. What they do is they just release off their electrons to get a full outer shell, and it builds what's called a sea of electron, which gives the ability for the metals to stay together, those ions, and it gives us the ability for us to shape, transfer electricity, all of that, all those properties that are specific to metals, ductility, malleability, luster, every bit of it is based off of that sea of electrons. So what you see here is like what they're trying to show is this metallic bond, or all these cations of those metals sitting in there, and all that blue around it, that's just that sea of electron. Those electrons are just freely flowing around there because they're sitting around a bunch of positive charges and they're just rolling around. So metal bonds allow metals to conduct electricity because some of the electrons move freely throughout the entire metal. Big, big, big important thing. Literally, how you get electricity in your house is based off of this. How we get electricity in our school, how we charge our phone, everything. Everything is based off of this. So then we have metallic bonding. When a force is applied to a metal, some of the electrons are pushed aside. This allows the metal ions to move past each other, thus deforming or changing the shape of the metal. All right, this is how, like the desk that you sit in, they have bent bars, and it's how, I'm trying to think of something, um, swords. I mean, any metal that we bend, any metal that you see bent, that's what is happening here because of that sea of electron. It gives it the ability to take that shape. So, talking about visualizing bonds, within this, pretty much as simple as to gain stability, they will share, gain, or lose electrons. They'll form ions and molecules. The properties of the metals can be explained by metallic bonding. So the change of one or more compound into another compound is a chemical reaction. This is like the really cool thing, uh, where I really like to make it in chemistry because it gets really, really interesting, really, really fun, really, really quick. But within this, chemical reactions, they're described by chemical equations. Okay, so the reaction taking place will describe it by a chemical equation. So an example of this is like making water. So I can take some hydrogen, some oxygen. There should be some heat here, but they don't show that. And then boom, we have water. We've taken hydrogen and oxygen, and now they've came together to make water for us. Pretty cool, right? So when you write a chemical equation, you must balance the equation by showing an equal number of atoms of each element on both sides of the equation. Reactant side's on the left, the product side's on the right. The same amount of matter is present both before and after the reaction. A way to wrap your head around this is like a campfire. So you have a wood log, take its mass, put it on the fire. Once everything's all said and done, you take the ash and you weigh it. You don't get anywhere near the mass that you had before. Why? That mass is still, this still exists because if you could capture all the gas that was released from it, you would have the actual mass of the log. There was a guy that proved this, and he proved the law of conservation of mass. He did this by taking a uh, iron pipe, and then he had created steam, pushed steam into the pipe, and he calculated out the mass of the water that was forming the steam that went through. He had the mass of the pipe before, and then he showed even the rust that formed on it. It was a reaction that took place, but the mass before and after the reaction of was equal to all the components added together. So of your what he started with and what he ended with was still accurate. And it was, I mean, it was done right before the French Revolution. It was a very, very, very intuitive um, experiment. So mixtures and solutions. So a mixture is just a combination of two or more components that retain their identities. And then you have a mixture's components are easily recognizable. It is called a heterogeneous mixture. In a homogeneous mixture, uh, also called a solution, the component, gosh, I hate that bell. The component particles cannot be distinguished, even though they still retain their original properties. A solution can be a liquid, gas, or a solid, does not matter. Then we have acids. Acids are really cool little guys because what they are hydrogen ion donators, or they're proton donators, because hydrogen ions have lost their electrons, so it's literally practically just a proton. And all this is, big fancy way of saying, is an acid solution containing a substance that produces hydrogen ions. This pH scale is based on the amount of hydrogen ions in a solution. If you've ever heard anything about the pH level of an acid, that's where this is coming from. Another one of these is bases. Okay, so a solution produces hydroxide ions in water. That is called a base, and that is also where we get the pOH scale. Not as famous as the pH scale, but there is a pOH scale. And that went a lot faster than I expected it to. But ladies and gentlemen, fast and quick, there you go. That is chapter 3, section 2 on combining matter. If you got any questions, holler at me on live grades. See y'all.